Welcome back to Physics 371 Online. We're starting a new chapter, Chapter 4, which deals with the effects that electric fields have when they're applied to matter. Thus far, we've spoken about producing electric fields in empty space, and then what effect they have on charges that happen to stray into the vicinity of the field. But what if the fields are applied to real, honest-to-goodness bulk matter? What changes does that cause in the matter? And then when the matter experience these changes, what effects do they have on their surroundings? So these are the kinds of things that we'll discuss in Chapter 4. And today we'll begin by talking about this phenomenon called polarization. When an electric field is applied to a piece of neutral matter, what happens depends on the electronic properties of the material. In conductors, the free electrons that are inside the conductors are free to move since they're not bound to any particular atom. And we've talked a little bit about this phenomenon already. In insulators, charges inside have less freedom to move because they are all bound to parent atoms. So it might seem at first that insulators don't really have any interesting behavior. However, the applied field, when it's applied to an insulator, can cause the charge distribution of the individual molecules to change in two distinct ways. It can either cause the charge distribution to rotate if the molecules have a permanent electric dipole moment, or it can cause the charge distribution of the molecules to deform or stretch if they don't have a permanent electric dipole moment. And we'll consider both of these phenomena. First, deformation, which results in the creation of induced electric dipoles, and then rotation, which results in the alignment of existing electric dipoles that aren't yet aligned. And we can show these two mechanisms schematically. First, let's look at the formation of induced electric dipoles when the matter not only is neutral, but doesn't have any net dipole. So when there's no applied field, here's a chunk of matter, and here we're looking at two molecules that don't have any positive or negative ends to them. They're not polar. When we apply a field, though, these atoms or molecules that do contain charges experience a separation of charge, and so they end up with a positive end and a negative end, and we schematically represent that with these sort of footballs here that have plus and minus ends. So where there were originally no dipoles, now we have induced electric dipoles in the material. Let's also look at what happens if matter has existing electric dipoles inside, but they're not lined up. And the reason that this might happen when there's no applied field is due to thermal agitation. The temperature of the system causes these dipoles to jiggle back and forth around some equilibrium position, and they don't experience normally a net alignment. But when we apply an external electric field, then these dipoles rotate and they line up with the applied field. And so what's interesting about both mechanisms is they end up producing an end result that's very similar. Both cases result in the creation of a polarization in the material. And we quantify this, we define a quantity, capital P, which is the polarization, and that polarization is defined as the dipole moment, lowercase p, per unit volume of material. So whatever units dipole moment has, divide that by a volume, and that gives you the units of polarization. As you can imagine, the dipole moment, lowercase p, is typically used to talk about the properties of an individual atom or molecule, whereas capital P, polarization, is used to talk about a chunk of macroscopic material and its polarization properties. All right, let's look a little bit more in detail at these two phenomena, and we're going to spend a significant amount of time here on this deformation process when there's an applied field that is used to impact neutral matter that does not have originally any dipole moment. So in a uniform electric field, a neutral atom experiences we can think of it this way, a displacement of its centers of positive and negative charge. So here is a neutral atom that has even distribution of negative and positive charge in a way that originally, when there's no applied field, means that there's no dipole moment. There's no real positive or negative end to this atom. However, when we apply a field, we can think of the centers of charge being displaced from one another, so that here the center of negative charge is still the center of this sphere, whereas the center of positive charge, in other words the nucleus of the atom, has been shifted. And I've greatly exaggerated the effect here just so that you can see it. This results, of course, since now there is a separation of charge, in a net dipole moment for the atom. And since the charge centers are displaced along the field direction, that is the direction of the dipole moment that's induced, parallel to the field. If the field strength is not too strong, then we can write a nice linear relationship between the induced dipole moment and the applied field. And the proportionality constant is the atomic polarizability, which of course depends on the properties of the atom. We can estimate this quantity. We'll do a very simple model here, and this is following what Griffiths does in the textbook. And then for homework, you have a problem where you're going to do a little bit more sophisticated calculation. But we can make a quick estimate by using a very simple model with the following assumptions. Assume that we've got a neutral atom whose negative charge has uniform density throughout the volume. And that's probably not a very good approximation, but it is a simple one to use just to get a rough idea of what the polarizability is. Then let's also assume that even though the positive and negative charge centers are displaced, that the atom retains a spherical shape, even when the field is applied, with a radius of a, and that the separation of the charge centers that occurs is small. So d is that distance, and we'll assume it's much, much less than the radius of the atomic sphere. So, just showing another schematic picture. For electric field of 0, we have a negative background charge, which we know is made up of electrons, and we're going to assume that they're uniformly smeared out within the sphere. And of course we have a center of positive charge, which is the nucleus. So that when there's an applied field, we get a net displacement here of the negative charge center and the positive charge center of an amount d. Now, why does this stop? Why doesn't this continue to be displaced until perhaps the electrons are completely ripped away from the nucleus? Well, there's an equilibrium that's reached. And what we want to do is think about the forces that the nucleus experiences. As a positive charge, it experiences a force due to the external field, but it also experiences a force due to the negative charge cloud of electrons. We can use Gauss's law to calculate the electric field that negative distribution of charge produces at a distance d away from its center. And so when the applied field and the field produced by the negatively charged electrons are equal and opposite at the location of the nucleus, then equilibrium is reached. And this allows us to set up an equation that will give us an estimate for the polarizability. So Gauss's law, I won't do the calculation here, but I'll remind you of the result. If we have a sphere of uniform charge density and a total charge q, then at a distance r away from the center of the sphere, the electric field, which in this case is the electric field of the electrons, is qr over 4 pi epsilon naught a cubed. All right, you probably recognize that result. And here what we want to do in order to obtain the equilibrium condition is evaluate this at r equals d and then set that equal to the magnitude of the applied field. Okay, because under those conditions then, this positive charge will experience two equal and opposite fields and therefore have a net force of 0. So qd over 4 pi epsilon naught a cubed is equal to the applied field E, and we can identify the term in the numerator qd as the dipole moment because it is the expression that's appropriate to a positive and a negative charge of equal amounts displaced by a distance d. So P, the magnitude of P, is QD, and therefore E is equal to P over 4 pi epsilon naught A cubed, and I can solve this for the dipole moment and see that we have just the kind of linear relationship between the dipole moment and the applied field that we expected. And so the proportionality constant is the polarizability, right? Alpha is simply 4 pi epsilon naught A cubed. Now, for something simple like the hydrogen atom, where the radius of the sphere is essentially the Bohr radius, so if we plug that value in, then we can evaluate this ratio, alpha over 4 pi epsilon naught, which is just A cubed, as about 0.15 times 10 to the minus 30 cubic meters. And in this sort of ratio format, that is an estimate for the atomic polarizability of hydrogen. Now let's compare this just to see if it's even in the right ballpark. Let's compare this with experimental results for some typical atoms. And what we see for this ratio alpha over 4 pi epsilon naught in units of 10 to the minus 30 meters cubed is that the values cluster somewhere between 1 or close to 1 and 10 for most typical atoms that we see here, at least lighter atoms in the periodic table. And so the 0.15 that we got for hydrogen is actually not a bad approximation. It's only off by about a factor of 4. And so the fact that it's even close, despite the relatively crude model that we used for this atom, gives us confidence that we actually are understanding at least the basic details of the physics that are involved. So it's not a bad approximation. And as I said, you'll do a more sophisticated one in a homework problem. So the other phenomenon, the rotation of an existing electric dipole, produces an alignment of these kinds of dipoles, and we'll just very briefly describe how that works. In a uniform field, the dipole will not experience any net force, but the field will exert a torque on it. And it's worth thinking about for a moment why there's no net force on this dipole. So if we have a dipole P, which points from negative to positive charge, and we apply a uniform electric field E, hopefully you can see why, if that field is uniform, it will exert equal and opposite forces on the positive and negative ends of the dipole, and therefore it will experience no net force. However, the forces that there are exerted on the two ends will not be exerted at the same places, and as a result there will be a torque that will tend to rotate the dipole. If it's free to move, it will tend to rotate it so that it lines up with the applied field. And Griffiths uses the symbol N for torque, I suppose because he uses tau for the volume element in spherical coordinates, but the torque N is given by the cross product P cross E. And we can also show that the potential energy of the dipole in this applied field is given by a similar expression, U is equal to minus P dot E. And so the cross product of P and E gives you the torque, minus the dot product gives you the potential energy. And we'll just note in closing here that the expression for U shows us that the minimum energy, the most energetically advantageous configuration, is when P and E are parallel, because then U will be most negative. If P and E are anti-parallel, then P dot E will be negative, and the U will have its maximum value. Okay, and so this makes sense. Having P parallel to E gives us the lowest potential energy, and it also would be the configuration in which there would be a zero torque. And so it's the lowest possible energy. And we'll be using these expressions to do some simple calculations on the homework assignment that you'll see in class. That's where I'll see you next. Bye.